Google's quantum computer ran the calculation. It processed variables that no classical system could hold simultaneously: the rate of stellar formation across observable galaxies, the acceleration of universal expansion, the decay timelines of matter at the subatomic level, the thermodynamic trajectory of energy distribution across the cosmos, and it produced a number, a date, not a range, not an approximation hedged with uncertainty intervals, a specific convergence point at which the conditions that define time as a meaningful concept cease to exist. The number it produced is 10 to the power of 10 to the power of 120 years from now. Write that out, and the digits would stretch further than the observable universe has space to contain them. It is a number so large that every framework humans use to comprehend large quantities breaks down completely before getting anywhere near it. 1,000,000 years is incomprehensible to human intuition. 1,000,000,000 years is further beyond intuition. 1,000,000,000,000 years is further still. And every one of those milestones, million, billion, trillion, is so vanishingly small compared to the number quantum AI produced that they don't register as meaningful steps toward it. They are rounding errors, noise below the threshold of significance. But the number is not the story. The number is the answer to a question. And the question, how does time end and what does the universe look like when it does, is where Google's quantum AI produced something that physicists are still processing. Because it didn't just calculate when, it calculated the sequence, the order of events between now and that final convergence point. And that sequence, laid out in the quantum probability modeling that Willow and its successors are capable of generating, describes a future so alien to current human experience that describing it requires dismantling almost every assumption about what existence means. The sequence begins with what we're already inside: the stelliferous era, the age of stars. Right now, the universe is doing what it has done for the last 13.8 billion years, forming stars, burning hydrogen, radiating light, sustaining the conditions that allow planets to exist and life to emerge on some of them. This era feels permanent because human timescales are so short relative to stellar timescales that nothing appears to change. The sun looks the same as it did 1,000 years ago. The stars visible tonight are the same stars visible in every human civilization that has ever looked up. The universe feels static because we are mayflies watching a glacier and concluding that ice does not move. The glacier is moving. Quantum AI's modeling of stellar formation rates across the observable universe shows the stelliferous era is already past its peak. Star formation is slowing. The universe's supply of cold hydrogen gas, the raw material from which stars condense, is being depleted and not replenished. The universe is not at the height of its stellar activity. It is past that height and on a trajectory of decline that will see the last new stars form approximately 100 trillion years from now. 100 trillion years sounds infinite from where we stand. On the timeline quantum AI produced, it is the first line of the first paragraph of a story with more pages than the universe has atoms. After the last stars form, they burn through their remaining fuel on timescales that depend on their mass. The most massive stars burn bright and die fast. Millions of years. Medium stars like the sun, billions of years. The smallest stars, the red dwarfs that make up the majority of stellar objects in the universe, burn so slowly and so efficiently that they will remain lit for tens of trillions of years after the last new star forms. The night sky, for any civilization that exists far enough into the future, will not go suddenly dark. It will dim, gradually, over timescales that make current cosmological history look like a brief introduction. But dim it will, and the direction of that dimming is toward a darkness that quantum AI's calculation traces all the way to its conclusion. When the last star burns out, the last red dwarf exhausting its hydrogen fuel and collapsing into a cold, dark remnant, the universe enters the degenerate era. This is the phase Google's quantum AI modeled with particular precision because it is governed by quantum mechanical processes that quantum computers model natively. The degenerate era is populated by the corpses of stars, white dwarfs, the dense cooling remnants of medium stars, neutron stars, the collapsed cores of massive stars that exploded as supernova. Black holes, the ultimate gravitational endpoints of the most massive stellar objects. And surrounding all of these remnants, in the vast cold darkness between them, are the remnants of planetary systems, dead planets, frozen moons, the wreckage of solar systems whose stars have long since gone dark. The degenerate era lasts longer than the stelliferous era by a factor that is itself astronomical. While stars burn for hundreds of trillions of years, the degenerate remnants they leave behind persist for periods measured in numbers that require exponential notation to write. White dwarfs cool slowly, radiating residual heat into the surrounding darkness, fading from white to yellow to orange to red to infrared to nothing, over timescales approaching 10 to the power of 37 years. Protons, if they decay as some physical theories predict, and quantum AI's modeling weights this possibility significantly, will have decayed entirely by 10 to the power of 40 years, leaving nothing but leptons and radiation where once there were atoms, molecules, planets, and stars. If protons do not decay, white dwarfs persist longer still, eventually undergoing quantum tunneling processes that convert them over unimaginable timescales into cold spheres of iron, the most stable nuclear configuration, before quantum tunneling again converts even those iron spheres into black holes through a process so slow it makes proton decay look instantaneous. By 10 to the power of 76 years, quantum AI's modeling suggests even the most stable degenerate remnants have undergone these tunneling processes. The universe, at this point, contains almost nothing but black holes and the slowly dispersing radiation of everything that has been destroyed. This is where the calculation enters the black hole era, and where Google's quantum AI modeling intersects with one of the most important theoretical insights in the history of physics. In the 1970s, Stephen Hawking demonstrated mathematically that black holes are not perfectly black. They radiate, slowly, imperceptibly by any standard that has meaning in the current universe, but continuously. Quantum mechanical effects at the event horizon cause black holes to emit radiation and lose mass over time. The rate of this Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes radiate faster and evaporate sooner, while supermassive black holes evaporate on timescales that are staggering even by the standards of the timeline we're already inside. A black hole with the mass of the Sun takes approximately 10 to the power of 67 years to evaporate through Hawking radiation. The supermassive black holes at the centers of galaxies, objects containing millions or billions of solar masses, take proportionally longer. The largest black holes currently known, with masses billions of times greater than the Sun, will take approximately 10 to the power of 100 years to evaporate completely. That number, a googol, the mathematical term for 10 to the power of 100, the inspiration for Google's name, is the rough boundary of the black hole era, the point at which the last black holes evaporate and the universe contains nothing but the diffuse, cooling radiation of everything that used to exist. Google's quantum AI ran the Hawking evaporation calculations with a precision that classical systems cannot achieve, because Hawking radiation is a quantum mechanical phenomenon requiring quantum mechanical computation to model accurately. The results confirmed the theoretical timeline but added detail about the evaporation process itself, specifically about what happens in the final moments of a black hole's existence. As a black hole evaporates and loses mass, the rate of Hawking radiation increases. The smaller it gets, the faster it radiates. The final moments of a black hole's evaporation are not a gentle fade. They are an explosive release, a burst of energy as the remaining mass converts entirely to radiation in what amounts to a quantum mechanical detonation. The last black hole in the universe will end not with a whisper, but with the most energetic event that has occurred since moments after the Big Bang. And then there is nothing but the dark era, the final phase. The universe, after the last black hole has evaporated, consists of photons, neutrinos, electrons, and positrons, fundamental particles dispersed across a volume of space so enormous and continuing to expand that the average distance between particles exceeds the current size of the observable universe by factors that cannot be meaningfully expressed. The temperature of this universe approaches absolute zero asymptotically. The density approaches zero asymptotically. The entropy approaches its maximum value asymptotically. This is the heat death, the thermodynamic endpoint that the second law of thermodynamics has been steering toward it since the first moment after the Big Bang. Time in the dark era becomes a concept without physical content. Time is defined by change, by one state of a system transitioning to another state. In a universe at maximum entropy, with no energy gradients, no temperature differences, no structures of any kind, no processes occurring anywhere, there is no change. There's no before and after. The sequence that defines time, the arrow that points from past to future, has nothing to point between. The concept dissolves, not because something dramatic happens, because nothing happens, and nothing continues to not happen, forever. The number Google's quantum AI produced, 10 to the power of 10 to the power of 120, represents not the moment the universe ends in any dramatic sense, but the moment by which every possible quantum fluctuation that could produce any structure of any kind in the remaining particle, soup has occurred and the universe has settled into a final state of perfect, permanent, absolute equilibrium. Even quantum fluctuations, the random, spontaneous appearance of particle pairs from the vacuum that quantum mechanics allows, become meaningless at this scale because any structure they produce immediately disperses back into the surrounding void. The universe reaches a state where not even quantum randomness can generate novelty. That state, according to the calculation, is the true end. What makes this calculation remarkable is not the number. Numbers that large are easy to write. What makes it remarkable is the path that quantum AI traced between now and then, The sequence of eras, the physical processes that govern each transition, the way quantum mechanical effects that are utterly negligible on human timescales become the dominant forces shaping the universe on cosmological timescales. Hawking radiation is undetectable today because black holes are so massive that the radiation is far too faint to measure. On the timescale of 10 to the power of 100 years, it is the most important physical process in the universe, the mechanism by which the last structures dissolve into the final darkness. The quantum AI calculation also addressed a question that physicists have debated for decades without resolution. Could life, intelligence, or information processing of any kind persist into the far future of the universe? The answer the modeling produced was layered. In the stelliferous era, the next 100 trillion years, the conditions for life as we know it persist and potentially expand. The universe currently has more habitable real estate than ever before in its history, and that real estate will continue to exist for time scales that dwarf all of human and pre-human history combined. If intelligence survives long enough and develops sufficiently, the resources available to it are vast beyond comprehension. In the degenerate era, life as currently understood becomes impossible. But information processing, computation, thought, experience in some form, might persist in systems built around the residual energy flows of cooling white dwarfs, operating at temperatures near absolute zero but not yet at it, processing information at rates so slow they would be imperceptible from our current temporal perspective, but potentially rich and complex from an internal perspective, where subjective time is defined by computation cycles rather than physical seconds. In the black hole era, Hawking radiation itself becomes an energy source, the only energy source. Black holes become the last power plants in the universe, and any intelligence that persisted into this era would be orbiting them, harvesting the radiation, existing in conditions so remote from anything in the current universe that the word life would be a metaphor at best. After the last black hole evaporates, the calculation offers nothing. No energy source, no structure, no mechanism for information processing of any kind. Whatever persisted through the previous eras ends at the boundary of the dark era, not dramatically, not with a final thought or a last experience, simply by running out of the physical prerequisites for any process that could constitute experience. Google's quantum AI traced this entire arc. From the current moment, inside a stelliferous era past its peak, through the long dying of the stars, through the quantum mechanical slow dissolution of degenerate remnants, through the Hawking evaporation of the last black holes, to the final dispersal of everything into a uniform, cold, structureless void where time has no meaning because nothing changes and nothing ever will again. The number it produced at the end of that calculation is the timestamp on that final state, the date by which the end has fully, completely, and irrevocably arrived. The reason this calculation matters now, to people living in the first trillionth of a trillionth of a trillionth of a percent of the timeline quantum AI just mapped, is not practical. It is not a warning about something to prepare for. It is something more fundamental. It is a complete picture. For the first time in human history, the computational tools exist to trace the physical trajectory of the universe from beginning to end with enough precision to map the sequence, identify the mechanisms, and calculate the timescales. The picture is complete in a way it has never been before. The universe began approximately 13.8 billion years ago. It will end, in the only sense that end has physical meaning, at a moment so far in the future that the entire history of the universe to date is not a rounding error on the way to it. It is less than that. It is a single Planck moment compared to what follows. Everything humanity has ever done, thought, built, destroyed, discovered, and forgotten, exists in the first imperceptible sliver of a timeline that extends so far beyond us that our existence is statistically indistinguishable from the very beginning. Google's quantum AI calculated the end of time, and in doing so, it showed us exactly where we are within it. Not at the middle, not near the end, at the very start. The universe is younger right now, relative to its total lifespan, than a human embryo is 1 second after conception. Whatever comes next, for humanity, for intelligence, for existence itself, there's more time ahead than the human mind was built to hold. The calculation is complete, the number exists, and the universe, indifferent to whether anyone reads it, continues its slow and patient journey toward the moment that number describes.